and let's get started to this Introduction to Machine Learning workshop. So let's go through the agenda for today. The first 4 agendas will be presented by myself, and the last 3 will be presented by Matthew. So in between these agendas, we will have Subcom show their code and how you can actually use them practically. Cool. So let's think about machine learning from a very simple and high perspective. So the first thing that you might want to think about is a game that we have played as kids and some of us in quant trading interviews. So the first one that we can think about is line games. So predicting the next number that comes into a sequence. As you can see, the next number is going to be 14 because of the rule being +3 from the previous numbers. So what machine learning is trying to do is very similar. It's trying to use the idea of data to try and learn a rule and create a prediction. As you can see in this case, it is 14. And from here, you can see that the data that we are given is being learned on, and we're trying to find a rule based on this data. So 2, 5, 8, and 11. And the prediction set is going to be 14. So from a very basic view, machine learning is the act of using statistical algorithms to find a function that best describes the data. And mathematically, we can write this as y is equal to fx plus epsilon, where epsilon is irreducible error. Okay, so the function is what we have learned using the data that we have been given, and y is what we're trying to predict. So that in itself is a very simple analogy of what machine learning is. But what exactly is machine learning? So machine learning is an algorithm, like I said, that analyzes data to identify patterns and make accurate predictions from intelligent decisions. So essentially, we're trying to find patterns in data. So there's 2 main types of machine learning. Number 1 is supervised machine learning, and number 2 is unsupervised machine learning. So inside supervised machine learning, we are given 2 main types. We have regression and classification. And in terms of an actual machine learning problem, it is very important to frame your question in terms of a regression or classification. So in this case, we have a regression which predicts a continuous number, like let's say amount of sales per year. Or we can predict a classification, so predicting whether a Boolean number, true or false, buy or not to buy in this example. So in unsupervised machine learning, we're given just a data set. As you can see in supervised machine learning, we're given a training data set and a test data set. So if we were to think about it in another analogy, it will be something similar to taking a test, for example. Everyone's going to do finals this year and this term. So our training is going to be testing on past papers, and our test data set is essentially going to be the final exam. And then the prediction result is how well we actually predict and go on the test. So unsupervised machine learning is going to be just trying to find a pattern that exists in the data. So for example, if Woolworths comes to you and says, I want to find the types of people inside my particular customers, right? We don't need to give it a particular training data set or a test data set, but we just give it a data set, and then the machine learning algorithm learns by itself. That is unsupervised. So an example is clustering, like market segmentation that I talked about previously in Woolworths. So when can we actually use data or machine learning? It's literally anywhere where there is data. And that is why machine learning is such a prominent field right now, because of how prominent data is and how available data can be inside every single industry. So from healthcare to banking to, I guess, whatever you can think of. So let's go on to the next slide. What is data cleaning? So now that you kind of have an intuition to what machine learning is, let's think about how we can get the data itself. Okay, so get the data available in a way that is good. The motto that I kind of live by is bad data gives bad predictions. So rubbish in, rubbish out. So the first thing that I want to talk about is how can we get a good data set? So my walkthrough is, let's use Kaggle. Okay? So I will give you guys, let's say like 1 or 2 minutes to get onto Kaggle. But essentially, let me show you around what Kaggle is before we look into how to find a good data set. So Kaggle is essentially a platform where good data scientists, really great data scientists actually, look into and do competitions together. So they are given a prize at the end. Let's say there are prizes up to $100,000. So if that doesn't motivate you, I don't know what will. So as we can see, there's a lot of competitions, data sets, models, and code and discussions where you can learn from others and continuously learn by yourself. So let's go into how we can find a good data set. Okay, so let's go onto the left here and click on data sets. And then we will go into filters. So how we can filter the data sets further. Usually I like to look for CSV files because they're the easier data types to work with. So I'm going to hit apply. And then one last filtering that I like to do is I like to filter on the most votes. These are the data sets which have been voted most by Kaggle users and by experienced machine learning scientists or data scientists. So this is actually how I found the data set for today. As you can see, today we'll be working on a water potability data set, which I have found using this particular method. So now that we kind of looked into how we can find good data, we can start thinking about how we can do imputations, as you can see, or outlier detections. So number one is for these missing values. So in our data sets, there may be values like infinity, negative infinity, corrupted values, or null values that can occur. So what can happen is what we can do is we can impute it with zeros, or we can impute it with the means, or by your ideas and different experiences, you can use different methods. So this is not an exhaustive list. So for our missing values, it is important to think about the particular context in which you're doing it. So in our particular example, we have a column called pH. And when we impute 0 into pH, let's say, that actually says it's going to be a very acidic water type. Okay, so you need to think about when we need to apply 0 imputing or in mean imputation. So the scenario is very, very important. So the next thing that I want to talk about is outliers. Okay, so extreme values and how we can actually detect them. So there is one single way that is really, really useful to us, and that is using the interquartile range and the quartiles. So from statistics, from high school statistics even, we can find the quartiles of a particular data set where the first quartile, second quartile, third quartile can be found. The interquartile range is going to be the difference between the third quartile and the first quartile. And this is going to allow us to find a sort of bound between the first quartile and third quartile that gives us the outliers. So again, this is not an exhaustive list. We have ways to find outliers using machine learning algorithms. This is called anomaly detection, but we're not going to go through this particular workshop with this. So I have included two main images that shows the impacts of outliers onto regression in the first figure on the left, and using interquartile range to find these outliers on the right. Cool. So these outliers can impact regression and impact machine learning algorithms in an unfavorable way, because as you can see, regression, which is literally the line of best fit, gets pulled up or pulled down significantly with outliers. Cool. So the next thing that I want to talk about is encoding. So essentially in a data set, we may have categorical data. Okay? So categorical data is a little bit unfamiliar to machine learning and machine learning algorithms. So in a statistical algorithm, we expect to see numbers. We expect to see numbers behave and how we calculate it, and we may do things like the MLE, which is finding the maximum likelihood estimator. So if we have text, it's a little bit difficult for the machine learning algorithm to kind of see or calculate these things. So that is why we introduce a few ways of encoding. So let's think about the data in itself. When the data or the category is nominal, or when there is no order or ranking inside the particular data set, we can use one-hot encoding. So as you can see below, inside the color column on the left-hand side, there is red, blue, and green. Okay, so there is no inherent order between red, blue, and green, right? It's not like red is first, or like blue is better than red, or blue is greater than red in any case. So that is why we consider one-hot encoding. For k unique values inside the particular categorical column, we create k unique features, and where 1 indicates the presence and 0 indicates the absence. As you can see on the right-hand side, there is now 3 unique features, 1 for each unique value inside the color column. Cool. So this is one-hot encoding, and there is another way called label encoding. So label encoding occurs when we have ordinal data. So ordinal data is essentially inside a categorical column, there is an inherent order within them. So for example, small, medium, and large. Let's say t-shirt sales. They can have small t-shirts, large t-shirts, or XL t-shirts. And in this case, we need to think about how we can preserve the information a little bit better than just one-hot encoding it. So as you can see here in the figures, in the teams on the original data, team A is the better team compared to team B, and team C is a worse team compared to team B. And that is why, to preserve the order, we have introduced 0, 1, and 2, where 0 is smaller than 1 and 1 is smaller than 2. And on the right-hand side, we have tall, mean, and short. And there is a particular order, as you can see, that exists within them. You can use tall for 0 or short as 2, or you can switch the order around. Tall is 2 and short is 0. The ordering doesn't matter, but as long as there is a particular order that is preserved, label encoding is useful. Cool. So next thing that we can think about is exploratory data analysis. And dare I say, this is just exploring the data. Okay, so as data scientists, you want to think about how we can use the data in a way, or understand the data in a way that is that can give us an insight into how we can use it. So how dirty is the data? What type of distribution is the data? And how can we kind of think about it and how we can feed it into the machine learning model? So these 4 types of things I like to really consider, these 4 plots. So the correlation matrix allows us to find similarities or correlations between particular features and particular predictors to the features. So predictors is what we're trying to predict. Histograms is just a density plot, or we can see the distribution of our features. Violin plots are essentially better plots of box plots, where it includes the distribution as well as a box plot. And there is pair plots as well. So on the right-hand side, we have a correlation matrix. I like to think about the correlation as being like 2 parallel lines. If you can imagine 2 parallel lines together, they have a very high correlation. And if we have perpendicular lines together, they have very low correlation, or even -1 correlation, because they're completely different. So I guess you can think about, let's say, connectivity to digital public services, which has a 0.64 correlation, as being not that high. So anything that is greater than 0.5 and close to 1 is very, very good correlation. And anything that is smaller than -0.5, but bigger than -1 is also very good negative correlation. So next thing that I like to think about is density plots. So this gives me an insight into the distribution of what I'm trying to model. Is the nature of this, let's say, the Airbnb apartments or the price distributions, is the nature going to be more of a lower price, or is it going to be more of a higher price? Can I see the skewness? So skewness is how far away it is from the center, and how, I guess, what can we do with this data, essentially? So with EDA, or exploratory data analysis, it's really important to form a hypothesis as data scientists, to think about how does this data actually relate to one another, essentially. At the end of the day, we want to create a very simple thought or an idea of why we're using machine learning. So the last type of plot I'm going to be demonstrating is box plot. This box plot, like I said before, allows us to calculate the interquartile ranges, which allows us to find the outliers. In this case, you can see how far the deviations is and how much variance there exists for each particular plot. And if there is a high variance, we may need to think about, do we need to use some data transformations? Okay, so that leads on very nicely into the slide of data transformations. So data transformation is, my definition there, modifying original data to improve its distribution, scale, or other characteristics. So that's cool, all that. But the most important thing we need to think about for data transformations is the idea of normalization. So normalization is essentially changing the data into a way that has similar scales to each other. So you don't want to have a feature that is super big and a feature that is super small. You want to keep the scales in each feature consistent so that the machine learning algorithm can learn much more efficiently in this case. So in this case, we have 2 different ways of doing normalization. That is feature clipping and standard scaling. So in feature clipping, we introduce a hard limit into the data. So the outliers are data that cannot go past 4. As you can see, there is a very, very spectacular data set here where the outlier is around 55, but most of the data lies within 0 and 5. So we can just cap the outlier at 4, and then we can go about our day, essentially. So this keeps the scale without blowing it out of proportion. So that's feature clipping. Next thing we can think about is Z-score transformation. Essentially, what happens here is the x-axis of the raw feature is going to be the actual price or the actual result, right? So by changing this or modeling this using a normal distribution, we find how far away each of these data points are from the mean. So this is the idea of a Z-score, right? And as you can see, you can calculate the Z-score using the data point minus the mean over the standard deviation. So as you can see, on the right-hand side, we've changed the scale from 5,000 to 45,000 to -1 to 4. And this makes it easier for machine learning algorithms. If let's say we're using it alongside the previous one, the rooms per person from 0 to 4, this allows it to be around the same scale and thus makes the machine learning algorithm understand something easier, okay? So this is two ways. There is one more way about data transformation. The first way is you can use a lambda that is not 0. That is a Box-Cox transformation. Or you can use a special case of this Box-Cox transformation where lambda is equal to 0, and which I like to use the most, which is the log transform. So this essentially stabilizes variance and allows us to meet assumptions. It also changes the scale in some way. So there's two main ways in which log transforms can be useful. The first one is normalization, again, changing the scales into a more reasonable set of values. So for example, as you can see here, the ratings are from 0 to 3,000, but taking the log ratings per movie, we change the ratings from 0 to 8, which is much more simple and much easier for the machine learning algorithm if we have the same set of scales previously. The next thing we can do is remove skewness. This is something I like because some machine learning algorithms require normal distributions when we deal with the algorithm. So yeah, if you want to remove skewness, the first thing I think about is log distribution. Cool. So let's move on to the first model of today. So even before we think about the maths behind a machine learning model, the most important part of a data scientist and for us is to think about how we can frame the machine learning model into a question that we can answer. So let's think about it from a case study point of view. Let's say KFC, right? I'm sure we've all eaten KFC at some point in our lives, I think. KFC is a fast food company that sells amazing deep fried chicken. So they come to you as a data scientist to understand and predict whether the customers will leave or return. This is actually a very reasonable machine learning question because it is something we can change into a machine learning question. So we can use something called a classification. So remember a few slides back, I talked about the two different types of machine learning as being supervised and unsupervised. And inside supervised, we are predicting using classification whether something is going to be true or false. So two Boolean terms. So we can frame this question in this way. Whether someone will leave, we give that a value of 1 or Boolean terms true. If someone will return to eat KFC, 0 if false. So that is how we kind of change a case study into a machine learning question. Okay, so this is a very simple classification question that we can use for logistic regression. So how this model works is this is a very complex function that kind of uses a linear model inside the sigmoid function. So what's going on here is PI is defined as the probability of success given the data. So in this case, we have defined the probability of success as someone leaving. Okay, that's a bit counterintuitive, but that's how we can define things. So PI is the probability of someone leaving KFC given the data that is present. And we can use the sigmoid function, and inside the sigmoid function, this beta plus beta 1, beta k, this is a linear regression. And we can use this linear regression to give us and transform that linear regression into a value that is between 0 and 1 that gives us a probability. So then after we find the probability of each person, whether they're going to return or if they're going to leave, we're going to have a certain threshold to actually create a decision, right? Because probability isn't really going to help us completely. We can say that if the probability of a person leaving is going to be greater than 0.5, then it's going to be true that person is going to leave. And KFC needs to think about how to retain them as customers. So And if probability is smaller than 0.5, we'll classify as false. So can we all see from here, we kind of have a reason for KFC understanding these different types of people. If they're going to be classified as leaving, they need to think about, let's say, how we can keep these people. And then that comes into the business perspective of things. How can we interact with these users to get them to stay or get them to not leave? So that's how we use machine learning in a business context. So I'm not sure if the image is loading, but okay, it's loaded on my side. So the logistic model is, as you can see, the orange curve. It's a transform. Because of this transformation, it gives us a range of 0 to 1. That's this little squiggly line there. And the linear model is the blue line, which is present within that sigmoid function, as you can see, the beta 0 plus beta 1, xi 1, all the way to beta k. So that is essentially the transformation that happens, and that is the probability. So the advantages of a logistic regression are it's simple and very interpretable. It seems like there's a lot of disadvantages compared to advantages, but let me say that simple and interpretability is very important in terms of a data scientist and how we can explain to clients or explain to KFC in this case why your customers are leaving. Being simple and interpretable is very, very important. So that is why logistic regression is used so prominently in this field. So some disadvantages are it is sensitive to outliers. So we need to remove outliers in our previous steps that I talked about. It requires a normalization of data. So it requires that the scales to be very, very similar to each other because this model kind of takes it in a distance calculation. So it calculates how far points are between each other. And that is why we need to normalize the data. And lastly, there is a linearity assumption that occurs with it, which may not perform as well with non-linear data. Okay, so I would like to hand it now to Jocelyn, our amazing subcom, to go through the plotting and EDA parts of her code. Cool. Can you hear us, Jocelyn?
Yeah. So right now we'll be looking at the data set. And so first, what we want to do is we will first import the necessary libraries. So for example, here, import matplotlib.pyplot.splt will help us to create plots and visualizations. So next, what we want to do is that we want to read a CSV file containing all the data related to water potability in this link. And then we assign it to df, which is a data frame. Right, so next, we have the meaning of the features right here. So we have pH value and basically what it means. And then we have hardness, solids, chloramines. So these are the columns in the data set that we want to analyze. And then we also have relationships that we may need to consider since they may be significant. And in this case, to whether or not the water is potable. So by typing df, we can see that the data set and that we can see that there are some missing values that need to be fixed. And then so what we do first is that we basically look at the number of null values in each column, and we can see that pH, sulfate, and trialomethanes have missing values, and that we have to replace these null values with mean, since as William has explained, we can't change it to 0 or else the pH will be too acidic. So we basically want to replace these null values based on the group or sample mean. So basically what we do is we group each column by potability. So one group being zeros and one group being ones. And then we want to transform each of these columns, so pH, sulfate, trialomethanes, to be mean when there is null value. So that's why it's filna here. And then we transform it with the mean. So next, what we do is we want to set the dependent variables to be basically all the columns in the data set that is not potability, and the independent variables, so what we want to predict which is basically plotability, to be the y value, so that basically the independent variable, and the axis one represents a column. So first, what we do is want to plot a histogram on the plotability in the data set. So we can see here that there is more water that is not potable than there is water that is potable, since there's a high frequency of zeros than ones. So we can see that there's in the data set there's more water that's actually not safe to drink compared to the fact that it is safe to drink. And this is of type category, since it's only zeros and ones. So next, we want to plot the histogram for each of the variables in the data set. So first, we set the structure of the figure plots to be tree by tree. And then this is basically so that they will be structured well. And then we go through each of the columns in the data set, and then and plot a histogram. So this is basically what the line does. So it will plot a histogram for each of the columns, like pH, hardness. And then after that, we just set the title to be the column, which is like pH, and then the X label to be value, and Y label to be frequency. So in the end, we just adjust it and show the plot. And it will look like this in the end. So this will be like each of the dependent variables that we want to analyze. And we can see here that we can observe the data better here. So for example, we can see the highest frequency, like for pH, it will be 7, around 7. And we can see the distribution as well. So for solids, we can see that it is right skewed. And then afterwards, we want to observe basically the correlation between the variables. And this determines how changes in like one variable are associated with changes in like another variable. And basically it indicates like the relationship between the variables, like how strong they are. And so basically this is what we do, is we do df.core, and then we plot it as a heat map with figure size to be 10 by 8. And then afterwards, we just show what the heat map will look like. And in the end, we can see that this is the heat map, and we can see that there's not much correlation between each of the variables, since they are all just mainly blue. And this just means that the redder they are, the higher correlation between variables, but we can see that they are all not really correlated. All right, so next, what we do is we want to look at the data set and just look at the following statistics, such as like counts, mean, standard deviation, mean, interquartile range max for each of the variables in the data sets. And yeah, so this just gives like a brief overview of what we are dealing with, and gives us a better observation of the data set. All right, so next, this is basically the same as last time, but now we replace the histogram to be a violin plot. And that basically a violin plot, what it does, it combines like a box plot and a kernel density plot. So it provides like a visual representation of the distribution of data across like categories. And so basically the width of each violin represents like the density of the data. And the central white dot here, it indicates like the median. So we can see for like sulfate, for example, that there is for sulfate that there is a significantly like higher frequency in the median compared to like the rest of the data, with like a sharper slope compared to like the rest. And then we can basically see the density better this way as well, and compared to like a box plot. So next here, it is the same structure, but we replace box plot with, we replace violin plots with box plot right here. And then in the end, we get this graph. So we can see the outliers over here. And then this is like the min and the max values. And then we can see here, this is like the median, and this is like the interquartile range. And here, we're moving on to scatter plots. So we do this with SNS, the SNS module, and using pair plots. So this will be like the scatter plots between each of the variables. And yeah, so basically, as you can see, there's not much correlation since they are all like grouped in clusters like randomly, and we cannot see like any trends for any of them. So yeah, there's not any much correlation between any of these variables. So yeah, we want to just double check it. And here we are just viewing basically a specific scatter plot between solids and pH. And yeah, so this is basically what it looks like between these two variables. And as you can see, we don't see any increasing or decreasing trends, and they're all just really clustered randomly. So next, we just want to make sure that there are no null values, no more null values in the data set, and you can see that it is empty. So yeah, that's good. So next, we want to filter the data to only include portability where portability does not exist. So for pH, as you can see, there is a significantly higher density in the median 7 when water is not potable. And then next, we want to just graph the data again. But in this case, this is when the data is filtered. So when potability is only 0, so we exclude all the ones when water is basically not potable. So we want to look at only those data. And this is basically the violin plot for that. And yeah, so basically we can see that we plot all the violin plots. We plot violin plots at all. So yeah, basically this is what it will look like. So next, what we want to do is that we need to make sure that the variable that we are predicting, so water potability, are balanced. So here, what we do is we just group not potable. So that's the data set, or we only include the data where potability is 0 and potable is when potability is 1. And we want to look at a number of data that is not potable and the number of data that is potable. And you can see here that the ratio is 1. So we don't really need to perform any transformations on this. All right, so now I'll pass it on to me.
Hey everyone. Thank you, Jocelyn, for such a wonderful presentation. Let me share my screen. Yeah. So you have theoretically understood the logistic regression model, right? So now we are going to better understand it by practically implementing it. So let me just summarize what logistic regression is. Logistic regression is basically used for the problem where there is binary outcome, that is 0 and 1, true or false, yes or no. For example, whether a student will pass an exam or not, whether or not this particular deal would be finalized or not. So questions like this can be solved using logistic regression. First of all, we'll start by implementing the particular libraries. For example, we are importing logistic regression library from sklearn.linear model package. So sklearn package helps us to perform machine learning tasks in Python, and it is very widely used package. So even if you're doing machine learning in Python, you will surely encounter this package. The second thing is that we are using a standard scalar library. So what standard scalar is that it's doing that is basically normalizing your data. So by normalization, I mean that for all the features, right? For all the features, for all the values, we have mean equal to 0 and standard deviation of 1. So we are basically having a normal distribution for all the values. And then we are fitting those transform data into our X features. Then we are using a train test split library to separate our data set into 4 different parts, 2 for training and 2 for testing. So for training purposes, we have X train and Y train, and for testing purposes, we have X test and Y test. Okay, so X train looks something like this. So these are all the features that are required to calculate the portability of the water, and the portability of the water is fitted in the Y train. Okay, and X test and Y test look similar to this. There's not much difference, but if you see that the values of all this are properly scaled, right? We have values between 0 and 1 for majority of data points, and it is scaled to a very specific decimal points. So this is the importance of normalization. If the values were scaled, then our accuracy would be a very good accuracy. After which, I'm importing the logistic regression library from this particular package. And I'm fitting my X train and Y train parameters into this logistic regression library. So now logistic regression have performed its operations on X train and Y train, and then we are going to test that particular operations against my X test. Okay. Now, the thing to consider is that it has never seen this testing data set. This particular model has never seen this testing data set. So whatever things that we are throwing at him is completely new. And we want to find that how well our model is performing against this hidden data set. So for that, we calculate the accuracy score. Accuracy score is nothing but the difference between my original values and the predicted values. And if you sum them all up, we would get somewhere around 62.86%. So you can see that this logistic regression model gave us an accuracy of 62.86%. That's good. That's not very bad accuracy score. So let's see what all features were being undertaken, or what all features were given more importance or less importance by this particular model. So you can see that this is a feature importance matrix, and it basically is telling me that these 3 features had a positive importance and the rest had a negative importance. So this feature number 2, right? Feature number 2 had around 3.4% positive impact on my model. Similarly, feature number 3 had around 3.2% impact on my model. So this feature importance matrix comes quite handy when you want to understand which features are working for my model and which features are not working for my model. Yeah. Now I will pass on to Matt to further explain you with more models. Matt, upon you.
Yep. Okay. Thanks, Meet. And just before I start sharing my screen, I might just want to, I guess, ask whether anyone can fill out their attendance forms. If you could, that could be really great. Yeah, thanks for that. So now that we've gone through, I think, logistic regression, which is quite like a linear, like equation-based model, now we want to go through something a bit different, known as random forest. So in terms of what random forest is, this is quite a bit different from, say, logistic regression, in that this is something that's known as an ensemble model. And that is, it takes the outputs of multiple models, aggregates them all together, and spits it out as just one single output. So as you can see in the figure to the right, we have, say, 4 different individual models, which are called trees, and we just average these together to get like one single output. And the key behind how this kind of model works is something known as wisdom in crowds. And that is that while one model can very much be quite susceptible to, say, individual error, it's very unlikely that every model is incorrect if they take, say, a majority vote. And that is that any individual error is ultimately evened out. Whoa, sorry about that. So I think
the key in terms of how this works is something called variant reduction. And that is in terms of like each model, you don't want them to all behave very similarly in that you don't want them to be correlated. And by correlated, I mean, if one say yes, then all the others might say yes, right? So that's what correlated is. If they're uncorrelated, they're all quite independent outputs. So therefore, if they're quite independent, then you kind of get that independence or that kind of wisdom in crowd mentality. And I suppose the pros and cons of random forest in that it's quite accurate compared to, say, logistic regression. However, the issue is that it gets quite hard to explain or interpret when you're sort of aggregating the inputs of, say, multiple models like 4 up here. And therefore, you can't really separate out the individual effects of each variable, right? So now that we kind of discussed how it works on a high level, let's kind of discuss what it's like in terms of an individual model. So the individual models are things known as decision trees. And I think how you can think about these are kind of like flow charts. So you kind of begin at the very top as kind of like a condition. So here it might say x2 is less than 60. And that's kind of a condition you impose. And if it's yes, you classify it as blue or like yes or something. And if no, then you sort of impose more and more conditions. And I think how this kind of looks in like a state space, if you kind of plot out your data, is that each split or each condition looks like a boundary. And with each boundary, you kind of get more granular in terms of your classification. So really, you just partition your data in multiple regions. And from there, you split variable-wise until you meet some kind of stopping criteria. However, the main thing is that there are some issues in that trees can be prone to something called overfitting or bias. And by overfitting, that just means that you introduce too many splits and the classification gets too granular or specific to that one data set. And what you end up getting is that since it's too specific, it doesn't generalize well to other data sets because of, say, like errors inherent in that data set. So by aggregating many models together, you sort of, I suppose, address that issue of like having one model be kind of too specialized. So in terms of how you aggregate the models and how you decorrelate them to get that wisdom in crowds, you sort of do that through 3 separate ways. So to start off with, we have bootstrapping, which is instead of using the same data set for each individual model, so out of all 4, you use all the same. Instead, you kind of create 3 or 4 or however many distinct data sets from that original set of data. And how you'll do that is beginning with your original data, capital Z, you'll sort of resample or pick with replacement observations from that data. And with those new data sets, you'll have, say, 3 new data sets that follow the same distribution, but are all kind of unique or new data compared to that original set. And again, that does things such as introduce variability among models. And again, you get that wisdom in crowds. Now, secondly, we have something called random feature selection. So again, picture those 4 individual trees. Well, if they had the chance to choose out of all, say, 10 predictors, they would all kind of make the same decisions when you're kind of making your flowchart splits, right? However, if you randomize their kind of choice of predictors or variables, say 5 random variables for each tree out of 10, then you introduce, again, more variation. And again, you get more uncorrelated trees. And again, you get sort of that wisdom in crowds. And finally, you can have something called height constraints, which again, imagine your flowchart. Well, your flowchart can go on for infinitely long and kind of become really granular or specific in classification. Now, how you can sort of prevent that really granular level of kind of classification is you just make a height constraint. So you cut off the limit at which you can keep sort of making those splits. And therefore, with these 3 methods, you can kind of make sure that the trees aren't going to behave all the same. And therefore, when you aggregate their inputs, any kind of individual error will all be kind of evened out by the end. So speaking on this, I think the kind of outputs that random forest can give is quite versatile in that it can be both a classifier or a regressor. So if it's a classifier, well, out of those 4 original models you would have seen, it will take like a majority vote. And from there, it will determine the probability that the model is say yes or no. And otherwise, if it's a regression problem in that you want like an actual number, you can just average the outputs and that's your final number. And in terms of implementation, you can use, say, the Bremen random forest function in the module sklearn and just implement this in Python. So I might just pass it on to Faris just to show you how to implement this function in kind of like a practical setting. So Faris?
Thank you, Matt. Yeah. All right, can everybody see my slide? Cool. All right. Hello, everyone, and thank you, Matt, for the explanation. So for random forest classifier, even though the basic concept behind it is pretty complex, the coding part is surprisingly easy. So what has been explained by Jocelyn and me in terms of implementation, we would want to first import our necessary libraries and use it for further use in the code. So one thing in particular that I want to highlight is the sklearn ensemble, which thankfully some amazing people has put down some codes of line to come up with this random forest classifier function that we can call anytime to do machine learning predictions. So again, we import the data and then we replace null values based on group mean, sample mean. This has been explained by Jocelyn, and we define our x and y variables in our data set. And then what we want to do is to split our data into two different categories. So we have the training data and we have the testing data. So by train test split function, where we call from this particular library, we input our x variables, y variables, and our selected test size. In this workshop, we particularly selected 33% of the data set will be the testing set, which means 67% of the data set will be the training set. And the random state is just a command to ensure reproducible results. It's not something that we should be worrying about so much. Then what we want to do is call our random forest classifier function, and we want to fit our x training and y training data set into it. And then as easy as that, what we can do next is actually predict our accuracy of predictions by this particular function right here. So what we want to do first is to take our selected model, which is the random forest classifier, and we use the predict function by imputing our argument called the x test. So essentially what this function do is taking the test function and it compares to our prediction, and it tries to predict from the testing set. And then we take the accuracy score, and what this function basically is trying to do is to compare the prediction from our model and find the similarities or the differences between the testing set. And then we print the function, we print the number, and we have about 78.92% of similarities, which is not bad prediction for a machine learning. And then there's another way or another approach to actually look at accuracy of our data set prediction. This is something we call as ROC curve. We can try to plot and see the values, or we call area under the curve. So ROC stands for receiver operating characteristic, and this will be explained more by Matt later on. But essentially what we're trying to do here is we use this function called the ROC curve and ROC AUC score. And what we want to do first is to try to plot the curve first. So what we want to input into the curve function is the testing data set and also the prediction that we try to do with our random forest classifier model. And then with this function, they will return three different parameters. So we have FPR, TPR, and the threshold. FPR stands for false positive rate, and TPR stands for true positive rate. And don't worry about it. This will be later explained by Matt. And threshold is something that we don't really use in this workshop. Okay. Using the matplotlib.pyplot, we can use this library to plot our data and to see how false positive rate is plotted against a true positive rate. And we use plot show to show our plot, and this is how it's looking like for this particular data set. Essentially, when you're looking at this curve, an easy way to interpret this graph is the further away this line is from this area, the better the prediction is. So what we're trying to do is to have this line as closer as possible to this to the y-axis. So if you can get that, it means your prediction is much better. With that, if we want to see numerically, we can use the ROC AUC score, which AUC means or stands for area under curve. And then we just, again, put in our y-test and y-prediction data, and it outputs a numerals, which in this case amounted to about 74.995% of similarity, percent of accuracy, which is not a bad prediction for random forest classifier. So that's basically how you implement random forest classifier in Python. I'll pass it in next presenter.
Yep. Okay. Thanks, Faris. So now that we kind of reviewed some of the models as well as, okay, so apart from like reviewing some of the models, we also need to be able to assess what is the actual quality of our model, right? So how we do this is through multiple metrics, and metrics are basically just ways to summarize, well, how well our model performs in certain aspects of model prediction. So here we're going to go through 3 separate ways, and we're just going to start off first with cross-validation. So with cross-validation, the idea of this is to separate your data into different partitions or portions and just test how your model performs on each different portion. So in terms of k-fold or LOOCV, what you do is just test on one portion and assess the accuracy of your model. So if I had to give an example, well, looking on the figure to the right, well, you'll see that in terms of your overall data, you've split that into, I think, about 10 separate pieces. And for 9 of those pieces, you'll just train your data or your model on that particular piece of data. But for that remaining piece that's still there, you would basically just test out that data and see how accurate it is, right? And from there, you'll basically just switch over in terms of which part you're testing. So in terms of all 10, you'll make sure you test all of those. And from there, you just aggregate all of those sort of accuracy scores together to get an overall indication of how well your model performs. And again, what this kind of does is it just kind of indicates predictive power on unseen data. I think it's particularly important when your test data is quite sparse, because I think in industry, you won't actually have test data a lot of the time. And instead, you'll just have like training data, right? Exclusively training data. So apart from cross-validation, that kind of looks at your predictive power, you'll also have something called a classification report. And the classification report delivers on a few different metrics. And I think here we're just going to talk about 2, one being precision and recall. Now, these 2 metrics both discuss very different things. And depending on what you want your model to do or what your problem is, you want to kind of emphasize different parts, or you might want to say emphasize a higher precision over recall. Now, in terms of what precision is, how you can kind of define it is when you predict something to be positive, so your model classifies it as yes, then you want to know how likely it is to be correct. So how likely it actually is yes. And how you can kind of think about it is this is how accurate your model is, right? So if it makes a prediction, it'll be very accurate in that sense. However, recall is a bit different to this, because what it is it's good at picking up positive instances. So it'll classify things as yes, even at the cost of false positives, right? So that means that if something is actually like, say, yes, for instance, like as classified, then your model will be able to pick that up. So it's very sensitive to that data. It might not be accurate because it might get it wrong most of the time, but it'll always pick that up. So you can imagine that recall is very sensitive. So it might be useful in, say, cancer diagnosis, whereas precision is a lot more accurate. So that might require a bit more nuance in your business problem. And finally, again, harkening back to what I think Faris said, is the ROC curve, right? So the ROC curve is just a curve that starts from the origin to all the way to 1-to-1. So the right-hand corner, the right top corner. And in terms of this, well, the y-axis is defined as a true positive rate. So that is out of those you predict to be correct and are positive, right? Ones that you predict are positive and are actually correct. Divide these by those which are actually positive, right? And whereas a false positive rate is just those which you predict to be positive, which is like incorrect, basically. And I think the most important thing is in terms of the actual y value, a higher y value is better because that indicates a higher true positive rate, right? So it indicates higher predicted correct positive values. So therefore, to maximize this kind of y value, you want to maximize the area under that curve, right? So going from yellow to green to blue, you're just increasing the overall true positive rate. And therefore, you can sort of measure this using a higher AUC, or the area under the curve, which indicates a more overall true positive rate, or just a better model quality. So to summarize, those are kind of just 3 different ways you can test the quality of your model, as well as the different aspects your model might test. And finally, I think that kind of brings us onto hyperparameter optimization, which is a bit different from like regular fitting to your model. So what are hyperparameters? Well, these are kind of parameters that just define the behavior or structure of the model. And how I would kind of think about this is they're parameters which are inherent to your model, right? So for example, in random forest, if you remember that it was an ensemble or an aggregate model, which takes multiple individual models together and averages out the outcomes, then the number of models you might use, so like 4, for instance, that's a hyperparameter. It's kind of inherent in the model and doesn't depend on your data. And again, this is kind of set prior to training because it's inherent to your model. And what that does is it kind of affects how your model learns over time. And I think the key as to why you would care about hyperparameters is that these are really important in terms of improving your model performance and efficiency, like beyond your data. So one way it does this is through controlling overfitting or underfitting. So in our previous example, overfitting was just kind of making too many splits and becoming too specific to one data set, and therefore it doesn't generalize well to other data. And therefore, if you kind of can control that, you'll basically be able to get better generalization on new data sets. So in terms of some of the techniques you can do to choose what hyperparameter to use, there are about 3 different techniques. So one is grid search, which is quite straightforward because you just define a list of hyperparameters. So imagine say 0 to 0.1 to 0.2, all the way to 1. Then you would exhaustively search throughout that entire list. And whichever one gives you the best model quality, you'll choose that parameter. Now, because this can be quite computationally expensive or exhaustive, you can instead do something called a random search. And that is throughout your predefined list, you'll just randomly choose whichever one gives you the best outcome just a few times. And through that random sampling, you'll be able to get what is an optimal parameter, right? So it's a bit more efficient. However, you can kind of improve a bit more on that because what you can do is you can use Bayesian optimization. And that is prior to actually choosing your parameter, you have an educated guess of what is the best parameter out of your list. So just choose whichever one you think is going to be best. And from there, kind of head towards a direction in which your model quality is improving over time. So that's kind of Bayesian optimization. It's a bit more directioned in terms of its search. And in terms of implementation, you can use this through grid search CV or randomized search CV, which I think Meet will be showing you at the end of this presentation. Right, so I think finally, just summarizing the overall workshop, I think it's quite important to kind of understand like what are the importance of like features or importance of variables, because this is ultimately what the model will end up communicating. So the main idea behind feature importance is, well, let's think about what is the degree to which an individual variable will contribute to the performance or quality of your chosen model, right? So for example, on our figure to the right, you'll see that certain variables such as petal width or petal length are quantified as much more important than, say, sepal length or sepal width. And therefore, it makes much more sense to concentrate on these when, say, doing data analysis or making decisions, or even constructing your models. So it's very important to understand which features are important. And in terms of some of the metrics, you can just say, think about the degree or the size of, say, coefficients, or there are other ways to quantify this. Right, and in terms of why we actually care about why features are important, I think one kind of technical reason is that it can be quite useful from a model perspective of things. So one is the quality or your prediction power. So for example, if you sort of choose what are the most important features to include in your model, that's often going to improve the quality or the predictive power of your model, right? So it's very good from a technical aspect. And again, it can also help with things such as interpretability, communication, or generalization. So if you know which variables are most important, those can be quite interpretable to anyone kind of looking at your model and understanding how that's being used, like how variables will actually, I think, feature in terms of your prediction. And finally, it can also help in terms of a real-world setting, in terms of business decision-making. So what is that? Well, it can kind of help with things such as simplicity, introducing some efficiency in real-world processes, as well as, say, allocation of resources. So a good example of this is you would have seen in your Colab code, the data was on potability, so drinkability of water, and you would concentrate on, say, what is the most important variable if you did want to sort of address that drinkability of water. So let's say contaminants was the most important variable, then you'll just focus on that, and that'll have a very tangible real-world outcome. So apart from these, you can kind of think about how you can quantify variable importance, and we're not really going to go through that too much. However, I think it is important to just kind of, introduce the idea a bit. So metrics you can use can include SHAP values or decision tree feature importance. Okay, so from this, I'll probably hand it off to Meet, who will take you through some of the practical applications of what I've been discussing. So thanks, Meet.
Thank you, Matt. Let me share my screen. Yeah. So now let's look upon the practical implementation of logistic regression. And as explained by Matt, we are going to use grid search CV and randomized search CV. These two libraries are being called from the sklearn model selection package, as explained earlier. So the gist of hyperparameter optimization is that if you want to understand hyperparameters, what do we mean by hyperparameters? They are basically configurations. For example, if you want to change the font of your text or color of your text, what you're doing, you are configuring your text. Similarly, in machine learning, we are configuring the parameters of a model. So earlier we looked upon the random forest model, right? Now, if you look at the parameters of random forest model, these are all the parameters of random forest model. There's max depth, max features, max leaf node, and estimators, etc. Similarly, for logistic regression, these are all the parameters. So have you ever thought that what happens if I change one of the parameters? For example, instead of 1, I write 100 here. What would really happen? That is what hyperparameter tuning is. You're basically changing the parameters of your model to better understand how it performs on the data set. So let's look upon the code of hyperparameter optimization. The main part of hyperparameter optimization is the parameter grid that I'm defined here. And in this grid for logistic regression, there are 3 main parameters: penalty, C, and solver. So let's look upon each one of them briefly. Penalty means that I want to minimize my loss function or my objective function. And I can do that by using regularization. I can use L1 method or L2 method or elastic net method to reduce my loss function. The second thing is C. Okay, so the higher the value of C, the more weight it would give on the coefficient of the training data. The lower the value, the less weight on the coefficients of training data. So often lower value of C is preferred because if we have less value of C, it would prevent overfitting and it would help us in minimizing the loss function. Then there is solver. So solver is basically used for optimization algorithm. So if you ever heard about gradient descent, which is a very widely used optimization problem useful for finding the global minima and minimizing the standard error. So that what solver is doing. It is calling this algorithms to basically find the best optimization algorithm. Now, let's look upon the implementation of grid search CV. So grid search CV is an exhaustive approach. By exhaustive, I mean to say is that grid search CV would perform its operations or the calculation on all the combinations of this particular parameter grid. So how do we calculate combinations? It's quite simple. We just take the product of each of this quantity. That is 4 into 9 into 5. So that comes about to be 180. So grid search CV would basically perform its operation on all the 180 combination, or I would like to say that it would create 180 logistic regression models for each and every unique set of hyperparameters. So you can see that why it is an exhaustive approach. This would take a lot of computational time and effort. So this is where randomized search CV comes to the rescue. Randomized search CV would uniquely select subsets of data with n combinations rather than going through all the combination. It would randomly select few of them and run its algorithm on that set of combination. So grid search CV takes mainly 5 parameters. The first one is the logistic regression model, this one. Second one is parameter grid. Third one is cross validation. The fourth one is verbose, that I want the output or not. And then there is end jobs. End jobs basically mean that I'm using my CPU core or not. That's it. So this code you are familiar with this. We are basically fitting the experience wide range. Then let's quickly hop on to the results. So this is the result of my hyperparameter optimization. You can see that there were 180 iterations. And of this 180 iterations, randomized search CV chose this as the best parameter of all, in which solver was Newton CG, penalty was none, and C value was 0.1. Grid search CV chose this as the best parameter. So you can see that C value is less than 0 in both of them, right? The less the C value, the better my accuracy would be. The algorithm for optimization problem is also the same, just that the penalty is different for grid search CV. And the accuracy score is not that different. They both have around 62% of the accuracy, which is fairly a good accuracy from our previous model. Previously, our logistic regression model gave us an accuracy of around 62.86%. So we're kind of in that range. So that's good. So we can see that this hyperparameter optimization is not giving us fairly higher accuracy as compared to our previous model. So we can tweak some of these hyperparameters in whatever way you like. Now let's just quickly glance onto hyperparameter optimization for random forest. So this is the parameter grid for the same. And the parameters are different for random forest because it has different underlying features. So let's quickly look at each one of them. N estimators would mean that the total number of trees in the forest, which I want, the more trees I have in the forest, the better model will perform. Then there is max features. Max features means that what type of method I'm using to split a node, right? Whether it is a square root method or log2 method. Then there is max depth. Max depth would mean that the depth of a decision tree, how many levels do I want in that decision tree. Then there is sample split, which means that minimum number of samples required to split a node, the parent node. Similarly, there is samples leaf, right? Minimum number of samples in the leaf node. So this samples means the data point in the node, not the features. Then there is bootstrap method, which was very well explained by Matt. that it is used for sampling subset of training data with or without replacement, whether you want to replace it or not, that's it. Similarly, I have also calculated the number of combinations that we're going to use. And you can see that there are 324 combinations. So grid search CV would run on all these 324 combination, and randomized search CV would just pick a random set from that and run its algorithm on that. The parameters are almost same. The new thing that I've introduced is scoring. Now you can write scoring based upon your need. You can have a R2 score, R1 score, whatever you want. I have imported scoring as precision and scoring as accuracy. Now, if you look at the results are same as before. There's not much difference, but these are the best parameters that are selected from randomized search CV, and these are the best parameters that are selected from grid search CV. Okay, and the accuracy score of grid search CV is around 79.7%, and of randomized search CV is around 79.2%. So accuracy score is also fairly good. From our previous score, which was around 78.92%, but we have a 1% increase in accuracy score. So we can say that our parameters are working in a positive direction. So this is it. This is hyperparameter optimization, and it's quite easy. The only difficult part is that the parameter grid, you have to define a very proper and concise parameter grid for your working of your model. Yeah. So I'll pass on to Matt to conclude this workshop.